So good afternoon, everybody. This is Eurostruct LiveTalk, and we are very pleased to have a esteemed speaker today. But before that, I would like to introduce myself. My name is Rade Hajdin. I'm president of the Infrastructure Management Consultants company in Zurich, Switzerland, and professor of structural engineering in University of Belgrade. I would very much appreciate if you can mute yourself because I hear the echo. Oh, thank you very much. I appreciate it.
Rather, you're muted.
Yes, I said I'm muted. I don't know why. Anyway, so sorry for these technical difficulties. And I'm very glad to introduce to you our today's speaker. Our today's speaker is Aleš Žnidarič. He's received his PhD at University of Ljubljana, and he's currently director of the Slovenian National Building and Civil Engineering Institute. He's a president also Brussels-based Forum of European National Highway Laboratories, or called FERL, a board member of the National Society for Weigh-In-Motion, or ISWIM, and a member of several national and international committees. He has over 35 years of experience in the condition and safety assessment of bridges, bridge loading, weigh-motion, and bridge monitoring. He has contributed to or led many national and international research projects. He was a member of the team that developed on the National Bridge Inspection and Condition Assessment methodology and led the project that developed the National Bridge Safety Assessment methodology and bridge weigh-motion technology. And before I yield the floor to Aleš, I would like to give you some information. Eurostruct, as you know, is a non-profit organization which deals with quality assurance with existing bridges and came out of the cost action TU 1406 qualification of roadway bridges standardization European level bridge inspect. At the same time, I would like to tell you that you can pose your question in chat. This is going to be forwarded to me, and then the answers are going to be given by Aleš at the due time. And this live talk is going to be recorded and will be available on YouTube as well. And with this administrative remarks, I yield the floor to Aleš. Aleš, please go ahead.
Thank you much. Thank you very much, Rade, for your kind introduction. Good afternoon, everyone. Maybe before I start, a couple of additional words about myself. I'm a bridge engineer who started in the period when we developed the bridge condition assessment procedures in Slovenia. And soon after, we started with safety assessment of bridges. And as a part of that, we were, of course, interested in bridge loadings, and that's how I got involved in bridge weigh-motion, which I'm working on for more than 30 years at this moment. So what I'm going to present you today is roughly this. So very briefly about bridge assessment and management. What is the motivation behind it? How do we measure heavy gross vehicle traffic? And then I will switch to structural analysis and bridge WIM. How can we couple those two methodologies, technologies, primarily by modeling traffic load effects on bridges? How do we measure some bridge KPIs with bridge WIM? And I'll demonstrate how this works with some case studies. And I will conclude my presentation with work in progress and some ways forward. So if we start by motivation, a possible question of a bridge owner can be how to sustain or improve the overall condition of the target percentage of the structures on my network, that they are rated as such or higher, so that they don't fall below a certain level of damage intensity. So the questions are, what is rated as good and acceptable? How the condition affects capacity and later on safety? how to assess or measure loads and performance of our bridges. And one important question, when to notify users about safety concerns. And of course, if we follow that curve on the right, we don't fall into that area which is too late. We don't want to do it too early. So we want to perform some kind of intelligent maintenance, which can fit into proactive, not reactive maintenance. And also, nowadays, we face a very important question, how to increase robustness. I will not talk about the climate change and its effects on our assets, but this has to be kept in our minds as well. I will focus today on this third question, so how to assess and measure loads and performance in bridge management. First, a few words about bridge assessment. I will just repeat the well-known facts, if you wish. What is the difference between design and assessment? And I think we can agree the design of new bridges should be conservative because, first of all, because uncertainties and changes of loads during the lifetime, because of decreasing capacity, and also all other unknowns during the lifetime. On the other hand, the assessment should be as optimal as possible because it's expensive to post, strengthen, or replace a bridge. There is some estimate around that adding 10% of capacity, 100% of capacity during the construction increases costs for 10%, while if you do it afterwards, it goes into the hundreds of percent. So obviously, it should be optimal. Capacity can be estimated from conditions and inspections, and also loading can be measured and monitored. And this is what we are going to talk about. And in addition, I will try to demonstrate how Weigh-In-Motion, and in particular bridge Weigh-In-Motion, can help in optimal assessment. Very briefly about structural safety of bridges. So basically, we want to ensure that the capacity is higher than the loads. And with bridge capacity, we have several challenges, especially with older bridges. We don't know exactly what materials were used, also how much material was used, in particular reinforcement, of which characteristics are these materials and where they are in our structures. Then I mentioned that the conditions change all the time, including climate. And we try to get this kind of information from archives, from field testing, from non-destructive testing, which is not done all the time. We see this procedure, and we name this procedure bridge assessment trio. So basically, you start with inspection of condition and its assessment. Then you move to some measurements and monitoring. And finally, you do structural analysis and try to get out as much as possible, as much as needed. Again, I will focus to the second item on this diagram. If I start with measurements and monitoring, what we typically do is material characteristics and damage extent monitoring and assessment. And we try to evaluate the actual loads. Actual loads, of course, change a lot. This is a typical truck from 50, 60, 70 years ago, which is a typical age of European bridge. Of course, this is far different to what we have today. Typical traffic jams on most of European motorways. We know that heavier and longer trucks are coming. We know that the truck platoons are coming, and they will both affect bridge loading. Not to mention the already today's critical situations like traffic jams on the bridge, and these beasts, bottom right, the cranes, which are the most difficult vehicles that we face on our bridges. And on the top of that, we have bridges which are deteriorating, and we have to combine those things to get a realistic evaluation of its safety, of their safety. Further questions that we have is how the loads are transformed into load effects, stresses, and strains, which we use in the analysis. It's not as straightforward as for payments, where they actually take axle loads. We have to first do quite a lot of transformations. We have to know how the loads are distributed across the structure. One thing is theory, the other thing is how it is done in practice. And also the dynamic amplification due to traffic loading is something that can be fairly optimized. Actual traffic loads can be obtained from any Weigh-In-Motion system, but there are some other things which can be obtained only from bridge WIM systems unless you instrument the bridge with specific instrumentation. But bridge WIM can provide also some things which are essential, and I will explain that in a minute. Also, some important questions that are affected by bridge assessment, which the first one is, of course, what is the condition of the structure? Then what is the carrying capacity? What are the real traffic loading, including dynamic? And what are the load effects? The first two are associated with condition assessment, and the last three with structural safety assessment. So why do we want optimal assessment? And the answer is pretty clear. We don't want to spend money for avoidable rehabilitations. If we do it in a conservative way, it's pretty obvious that we will do more than it is needed. Fortunately, bridges are stronger than we think. And I will give an example. This video was taken already 12 years ago, when we did a load test, a proof load test on a bridge, which was replaced afterwards, because the conventional analysis showed that the bridge is under design and it has to be replaced. And you will see that we have put on it more than 70 tons in the Eurocode configuration, so with two axles spaced 1.2 meters apart. And the result was pretty clear, that even with such high loading, there was a crack of 0.15 millimeter, but this crack closed after the bridge was unloaded. So clearly, the capacity of this bridge was much higher than calculated. So that's very important that we try to do as much as we can if we have to make a decision whether to close or even replace a bridge. In addition to the capacity, load effects are less than in the codes. I will show in a minute how load effects that we calculate from the measured traffic is far lower than what we have in design codes. So our bridges are very likely safe, but the challenge is how to prove that they are safe. And another important thing is how to recognize critical details, and that's where engineering judgment and experience come into the play.
Mm-hmm.
If I just focus on those old bridges, which are now more or less majority in our world, is that the first thing is that they were designed for lower traffic loads that we have today. So I showed some photos before. Loads are quite different from country to country, 40, 44, 50 tons, even more in some countries. Oops, sorry for that. What we know from the old bridges is that for today's loading condition, they lack of shear resistance, that sometimes they have low redundancy, in particular if they have Gerber joints, and we had some bad cases in the not that far history, when those bridges collapsed. They have inefficient reinforcement layouts, especially with skewed bridges. Those who inspect bridges have probably noticed that in the corners of skewed bridges, there are more cracks than we would like to have. Of course, there is low corrosion protection of post-tension tendons because of poor grouting and things like that. There are insufficient fatigue details for high loadings that we have today. Critical thing is decay of stone, masonry, arch bridges. A bridge on the photo can be very strong. You can hardly destroy it, but if there are some details, some fallen out bricks or stones, this can be critical. So fortunately, these bridges, despite the age, are generally robust, but I focus on generally, so this is not for all of them. Another problem we face with old bridges are the changing design rules. I have this example from Slovenia. We have 2,700 bridges on the state roads, of which 33% on the motorways and 56% on the state roads are older than 50 years. The problem is that we have changed in these 120 years 8 bridge design codes, starting with the Austro-Hungarian code from 1904, and then many others from the Kingdom of Italy, Kingdom of Yugoslavia, Kingdom of Yugoslavia with dynamic amplification factor, 2 codes in the former Yugoslavia, then we use DIN, and then finally Eurocode. So it's very, very important when you do the assessment when the bridge was built, and this information is quite often not available. So basically, for our case, we have 60% of bridges on the state roads and 1% of bridges on the motorways, which are by definition under-designed. And if we would perform the conventional assessment, we would have to spend an enormous amount of money to bring them on the today's standard level. In addition to that, the capacity is reduced due to deterioration. And what is even more important is that we have, and this is information that I get from also other countries, is that information is very limited for municipal bridges. Very often, or at least if I speak for Europe, we have generally very good information about state roads and motorways, but if we move to the municipalities, it's a completely different story. So now I move to the other level, to the other side of the safety equation, and this is loading, and particularly heavy gross vehicle traffic and its effect on bridge assessment. So how do we measure heavy gross vehicle loads? The most common technology still is traffic counters, which are everywhere. These are those inductive loops that you can see in the pavements. The problem there is that they provide absolutely no information about the axle loads. They just count the vehicles. This is something, but far from enough for what we need. So we know, or we have several weighing systems. The most common, again, are the static weighing scales, which are also quite common. But they are completely useless for traffic load monitoring because they are limited to very specific vehicles which don't provide comprehensive information about the traffic loading or our bridges. So we basically have to do what is known as Weigh-In-Motion, which, okay, this is the typical static scale. So we have to do Weigh-In-Motion, which is again divided to low speed, which is on special lanes beside the main roads, and it is done under control condition. It is faster than static weighing, but still not fast enough to collect traffic information. So we basically have to do high-speed Weigh-In-Motion, which is again divided to pavement WIM and bridge WIM. And in addition to that, we also have the onboard weighing systems, which are more and more common on modern trucks with air suspension. They can have included into the suspension system the weighing, and in the truck, in the cabin, you get information about the weights, as you can see in the center of this dashboard. So what are the high-speed weigh-motion systems? So all weigh-motion systems measure dynamic gross vehicle weight, axle loads passing at highway speed and uncontrolled conditions. So two important things: highway speed, so no stopping, and uncontrolled conditions. So nobody is controlling how the measurement is performed. And as a result of that, they do not weigh vehicles, but they calculate the best static load approximation. That is important to know. All weigh-motion systems provide axle loads and gross vehicle weight, number of axles and axle configuration, vehicle length and axle distances, speed, vehicle class, and then based on the technology, many other parameters. First weigh-motion systems were developed in the late 1950s, and there was a boom of development in the 1990s. And today there are more and more applications, including, or should I say in particular, related to bridges. And there are lots of universities around the world studying new approaches and different applications. This is the basic principle, generally quite simple. So the bridge WIM is measuring device that uses an existing instrumented structure, which can a bridge or a culvert, to weigh road vehicles or trains in motion at normal operating speed. So basically we instrument existing structures. In the past, there were lots of questions, whether do we have to build a bridge? Of course, we do not have to build a bridge. We use existing bridges, existing structures, we instrument them and use the algorithm that inversely calculates the axle loads that caused the bridge response that we measured. Bridge weigh-motion systems are over half a century old, or almost half a century old, the basic principle. But the main research was done in the 90s within the two European projects. The first one was COS323 and the WAVE. And those two projects resulted in the ISWIM bridge weigh-motion system that is today marketed around the world by the Slovenian company Cestel, which had more than 5,000 installations in more than 30 countries until now. It's based on the strain measurements. So this is a typical strain transducer. Transducers are placed either on the individual beams, as you can see on the photo below, or equidistantly over the width of the slab, and the direction of traffic is from the left to the right. Today, they are used and also developed in Europe, both Americas, in Asia. And the main benefits compared to the traditional pavement weigh-motion systems are that they are portable, which means that you don't disturb the traffic, which is a very big issue with today's traffic, especially in those motorways which have really dense traffic, and you can wait for months to get a roadblock that you can install or repair the system. So that's very important. And as I will show later, because you can measure bridge performance under the traffic and thus improve your bridge assessment. This is a paper that we wrote and describes bridge weigh-motion in many more details. I'm afraid that today I will not have more time to go in more details. But the principle in general is rather straightforward. We measure strains which are proportional to the moments, and we also can calculate the same bending moments by multiplying the unknown axle loads with the known position of the vehicle, known speed of the vehicle, and known influence line. remember the influence line, because this is one of those parameters which is also important for bridge assessment. And what we basically do, we minimize the difference between the measured and calculated moments, which you can see on the figure below. And if you have a match like this one, so the red is measured, the blue is calculated from those influence lines multiplied by the axle loads, you know that your influence line is a good one, or as good as it can get. These are some typical installations. Okay, I don't know what happened. I apologize for that. Typically, bridge weigh motions are installed on short to medium span bridges up to 30-35 meters. So beam bridges like the two on the top, or the slab bridges like the two on the bottom. But you can also do it on some other bridges. This was done on the Viaduc de Millau in France. I'm sure you know this bridge. This was done on the orthotropic deck bridge. This was actually the first installation on such a bridge. In another project, we did the first railway bridge WIM application, and also on the first truss bridge. This was an interesting endeavor, because it was the first time that we weighed trains. In another project, we instrumented another orthotropic deck bridge, which was used for what we call the virtual monitoring, which means that the numerical model of the bridge is so well optimized that you can perform measurements also in places where there are no sensors. This is a very promising technology, which can improve the assessment. And just recently, we performed measurements on the Noordijk Bridge in the Netherlands as well, which we know for years that they have issues with the insufficient capacity of the orthotropic deck bridge. And this was associated with bridge monitoring. Then in the last few years, we also did more measurements on the railway bridges. So these are two examples from Austria and Italy that were performed in the Assets for Rail project. So now, how do we couple structural analysis and bridge weigh motion measurements? I said before that the important thing is what's the actual traffic loading, and this can be obtained by all weigh motion systems, pavement and bridge weigh motion systems. But bridge weigh motion systems can measure 4 additional parameters. So first of all, strain records under the traffic loading, so you can directly couple the response of the bridge under the traffic loading, because of course we use the same strains for bridge WIM as well. And from these records, we evaluate influence lines, traffic load distribution, and dynamic loading. And I will show now how these things can help. Important thing as well is that traffic loading changes with time, so we have to consider that. And also, okay, this I said already, this is a redundant slide, so I will skip it. Modeling traffic load effects of bridges, there are many methods available. What we need are traffic loads converted in load effects. So in this case, you have bending moments which were converted from X loads using the influence lines. And what we are interested in are the extreme loads. We don't care much about those regular loads. We need very good data about the extreme loads. Then there are different methods from the extreme value distributions on the bottom, convolution method on the top, which should give similar results. Some authors are using long-term simulations instead of that. And the main objective of this exercise is either to develop the site-specific loading schemes, which means that we have data measured on a specific bridge that we would like to optimize. We can adjust the alpha factors from the Eurocodes or develop the rating, or sometimes called assessment loading schemes, which are more appropriate for assessment. And we can also use this data for fatigue load assessment, of course, using other methods that are available. One important question is how much WIM data do we need for the bridge load modeling? We did that some years ago with a lot of available Weigh-In-Motion data. And it turned out that a safe amount of WIM data is 100,000 heavy load vehicles. If you go below 50,000, you will severely underestimate the loading. It's conditionally acceptable between 50,000 and 100,000, but you have to be aware that you will be still underestimating. This is for the bending moments, and very similar situation we got for shear forces. So a very straightforward advice is, if you do this kind of assessment, collect at least 100,000 heavy gross vehicle loads, so axle loads and gross weights. And axle spacings, of course, because this also influences load modeling. So how do we now measure bridge performance under traffic? Typically, what is done is that we do some numerical models that we try to optimize as much as we can, but also a very common procedure is to do load test verifications. In particular, diagnostic load tests, which means that we load bridges to 60, 70, 75% of the design load, as much as it is achievable. On this bridge, we used 48 trucks. And if I fully loaded, actually even overloaded trucks, and if I remember correctly, we only achieved 65% of the design load. And this is the purpose of the diagnostic load test, is to verify how your model, how your design was correctly done. What we did in many European projects, starting in Samaris, which started in the late 1990s, until Bridgemon, which finished some 10 years ago, is that we tested how we could use bridge Weigh-In-Motion systems to obtain similar information than with traditional diagnostic load tests. So apart from the actual load testing, we measure influence lines, lane factors, or girder distribution factors, and dynamic amplification, and we named that soft load testing. So this is basically a lower level diagnostic load test, lower level because the load levels are much lower than with the traditional diagnostic load test. And for that reason, it's only appropriate for checking of the serviceability limit states. The typical example that we face very often, I must say, is that the bridge owner asks, I have this and this traffic on my bridge, is the bridge still safe? And in such cases, we can, in a very elegant way, demonstrate whether the bridge is safe or not. I mentioned the influence line. This is, in this case, used as a key performance indicator, but influence line itself is a key parameter also for bridge Weigh-In-Motion. Basically, it uses the same approach as for calculation of loads after you already have the influence line, but in this case, influence line is also an unknown, which is calculated. And the approach we developed is with cubic splines that describe the influence line. And this is again minimized to get the best possible match. And this is done for hundreds and hundreds of different vehicles that cross the bridge. And this influence line is calculated for each of these events. On this figure, you see an example of 528 different crossings. In blue, you have the mean influence line in this case. and the gray lines are standard deviation of this influence line. So in this case, I must admit, this is a very good case. You can see that this distribution is very low. And I must also say that this is converging very rapidly. So after 10 or 20, 30 calculations, your influence line will be very close to the final one. This is described in more detail in the paper that I'm showing down at the bottom. But the point is that when you have, if I name that, the accurate influence line, that also the match between the measurement and the calculation is very good. And if you have such a good match, you can be also pretty certain that the X loads that were calculated from this are very close to the actual ones. So this influence line is then used to set up the ISWIM system and also to calibrate the structural models. This is an example how this is done. This was done in the US on the typical underpass of highway. It's interesting because this underpass had a a steel hinge here. So you would expect that this would behave like a theoretical, simply supported structure. In addition, this bridge had a very poor access to the bridge, so we expected very high dynamic amplification because of that. So influence line in theory for this 27-meter long bridge should be like this, but based on the measurements, we got a slightly different situation. This was again calculated from hundreds of loading events. And then it's very easy to update your structural model that it corresponds to the measurement. This I'm showing here is a very simply straightforward 2D model, but you can do the same thing on model of any complexity. So there is no limitation about that. According to my experience, I can say that it is always different than in theory, because if it's not like in theory on this case, which is really simply supported with a steel hinge, then you can imagine then on some other bridges with more issues around the supports, the differences are even bigger. Again, you have a reference down there, but the result of this was that on this particular bridge, the actual bending moments are only 70%, 77% of the theoretical ones if we use the theoretical influence line. And in the extreme case, over the last 20 years, we got several cases which were below 50%, in the worst case, even 45% of the theoretical influence line. So that is substantial. And if you use this in your bridge assessment instead of theoretical values that you get, you can imagine that the savings are substantial. Similar thing is with the load distribution. So there are typically two approaches. One is the girder factors. So you go girder by girder, like in this case. 6 girders, you can see the measured distribution. Some people use lane factors. The important thing is that there are again substantial differences between similar bridges. You can have a slab bridge and you have another slab bridge which is very similar, but the load distribution, the measured load distribution can be different. So again, savings because of the actual values and because of the higher reliability of the data that you are using. Dynamic response of the bridge is also something which I think we are all aware of. Again, the same bridge from the US with one truck, very high dynamic amplification. Another case, 2 different trucks, again high but lower, with 2 similar trucks, extremely high, but if you have the extreme loading with a load crane, then the dynamic amplification is practically 0. This is how we calculate dynamic amplification. So basically, we use the most traditional approach. So static total load effect versus static load effect. Static load effect we approximate by filtering. Again, this is explained in some papers. But the important thing is that we again, for practically every vehicle crossing, we get the dynamic amplification value. This looks like this. This is the example from the same bridge, 5,000 DAF values. And you can see when you compare to different design methods that when you go to the extreme loads to the right side of the diagram, these DAF values go down to 1, which highly corresponds to theoretical calculations like the Danish reliability-based bridge assessment guideline, which was published many years ago. They have calculated a similar curves. With measurements, we can measure that. What we did was we evaluated 17 data sets from 17 bridges from the US and from Slovenia. They were differently populated from a couple of hundreds of values to almost 750,000 DAF values. And we, if we plot that on the same diagram, we had to convert gross weights to percentiles that we can compare values. We get very nice linear relationship with weight. And what is important is that even at the worst bridges, those values went down below 1.1. And that again, if you can measure that, there is another saving in your bridge assessment. So this is, we can conclude in line with theory. The issue is how to implement this in the codes, because I'm not aware that anyone would be implementing that to be available for general use. Again, the paper below gives more details about how we came to these results. To summarize, if we have the true traffic loading, this will have a positive effect on bridge safety because it will decrease the loading. Because we have the actual influence line instead of theoretical ones, it will again decrease the moments. Of course, it will slightly increase the shear forces in short span bridges, but that's far less evident than the moments. And dynamic amplification loading will go down, which means that bridge safety will increase. And this is basically how we can show that some, in particularly old bridges, are still safe for the modern traffic. I mean, this is basically that more reliable information we have lower uncertainty of results, which also influences the safety factors that we use. But we also have to point out that all these measurements are site-specific and also time-dependent. So this also has to be taken into account, but I didn't have time to talk about that today. How we implemented that, so this is the case study from Slovenia. In Slovenia, we don't have any assessment code. We just prepared the recommendations some 25 years ago, the first edition. We updated that some 15 years ago, in particularly because the level of loading increased tremendously after we joined the European Union in 2004. The approach we used is the rating factor, which originates from the United States and is used also in many other countries. So basically from the resistance, we deduct the dead load effects and we divide that by the live load effect, and what we get should be greater than 1. As I said, we developed the loading schemes, which we updated after the heavy increase of traffic some 15 years ago. And we also developed procedures to select safety factors for the dead load and live load. The dead load one is affected by the source of data, basically. So if we have the data, if we have just the design, or if we go to the bridge and measure everything. Live load effect, safety factor depends on whether we measure things like load effects, and factor 5 for capacity reduction depends on the condition of the structure. So in years 2006 and 14, we did 154 assessments of bridges that during the inspection proved as very bad or critical. When we performed the assessments, just by using the approach that I described without any measurements, we have shown that 118 of those bridges were safe. So we performed in-depth analysis, including soft load testing and detailed analysis only on 36 bridges, of which additional 36 were proven safe, and only 13 bridges were later posted, strengthened, and finally replaced. If we talk about costs, the replacement value of all 154 bridges was estimated more than 100 million euros. After initial safety assessment, this cost was reduced to 36 million. And finally, after all those procedures were performed, the 13 bridges cost was roughly 9 million euros. Of course, the value of the analysis that performed was way lower than the cost of savings, because we did this kind of analysis. And not to mention that indirect costs are at least twice those of the direct costs if you have to close the bridge or replace it. So work in progress, ways forward. This is a very brief information. What we do at the moment, especially the PhD student Doron is working on improving the finite element model updating. So we have a heavily instrumented bridge with more than 200 sensors, in particular strengths and accelerations. He did a very detailed structural model. So we have a digital twin, which can be used also for this virtual monitoring that I said before. So the bridge is now so well developed, the bridge model, that it can be used also for other conclusions that we can get from the assessment. He divided his work in 3 stages. The first one is just using bridge twin system strain measurements for finite element model updating. So based from that, he used 55 different calibration vehicle crossings, and he calibrated his model, where he showed that, of course, as expected, the stiffness of the bridge was underestimated, and there are roughly 20% savings just in the stiffness of the bridge. In his second stage, he included a more traditional measurement of acceleration. So he defined 3 variables that he wanted to calibrate. One are the main girders, the mid girders, the outer girders, and all the rest. So the deck and the safety barriers. These were the 3 variables. Then he calculated modal parameters from the measurement, acceleration measurements, and all the strains under the trucks, which are measured as permanent monitoring of the viaduct. And what he performed was error domain model falsification approach. This is methodology which is relatively new for bridges. Basically, the point is that you assume that the models cannot be fully validated by the data, but you say that instead they can also only be falsified by defining the range between the measurement values, and then you perform a number of different combination of all your variables. He did about 2,000 different cases, and what you see in the blue in the middle are those 7 out of 2,000 who fit all the thresholds of all measured parameters. This is very much in line to what he also obtained from the first stage, what was the strain calibration, which means that basically some parameters, the parameters are generally 20% underestimated, but here you can clearly see how those parameters affect model parameters and also strains. In the next stage, he will continue with basically a step backwards. So how to use the bridge-WIM influence line to update the finite element model using all the knowledge from the stages 1 and 2. Measurements were done. So again, this was on another bridge. Influence lines again show that the bridge is stiffer than the theory. And now we will see how this will be implemented in further analysis. Another project that we are working on is using artificial intelligence in improving, in particular, detection of vehicles, because I mentioned before that those measures are unattended, so you can measure all kinds of different things. And we also know that identifying incorrect axle configurations can lead to wrong bridge-way motion results, and as a consequence to errors in bridge load modeling. So we are performing in particular image recognition and machine learning procedures, and I must say that the first results are really promising. The vehicle classification has improved quite considerably, so we are looking forward to the results of that. What we will also do is we will have a trusted data repository published somewhere that also other researchers will be able to further improve the vehicle recognition algorithms. So if I summarize my presentation, I think we agree that if we perform bridge management, it's too costly to replace all problematic bridges, so we have to do what we can to optimize the assessment. It's also clear that we have some challenges of collecting quality data, but I dare to say that almost any measured data is better than no data. It's also well known that a lot of data is already available. Probably too much data is available, but we don't do enough out of it. And I hope that I have shown that bridge-WIM data is useful in this process as it reduces uncertainties. And of course, as a consequence, it saves with measures that we perform in bridge management. I cannot stress enough that engineering knowledge, judgment, and experience is important, because if you just do measurements and structural modeling, all kinds of questionable things can arise. So you must be able to perform a proper judgment of your results. And I mentioned 2 very promising techniques that are being developed, and which we hope that it will further contribute to the knowledge in this area. I can also point out that this is slowly becoming part of assessment guidelines and codes, and the new YAPMAS FIP recommendations guides that are under development will also include a great part of the topic that I have explained today. With this, I thank you for listening. I was only 5 minutes too long, so I hope that you will still have time for some questions.
Of course we do, Aleš. Thank you very much for this excellent and invigorating talk. And I guess a lot of people are really eager also to pose questions. We have already some questions here in the chat, and I would like to encourage everybody to pose questions in the chat in an available time that we have. And I will start by a question which came from Goran Milutinovic. He says, does WIM system, generally speaking, pavement and bridge WIM, have problem with capturing correctly the traffic jam loading scenarios?
Very good point. Weigh-In-Motion systems in general do not work in jam scenarios because practically all systems, pavement and bridge WIM in particular, they need a certain constant velocity over the sensors being those sensors built into the pavement or in our case, the bridge. So if you don't have a more or less stable velocity or constant velocity, the readings or the results will be more or less useless.
Thank you very much for that. We have another question from Marian Lvovsky. Thank you for excellent talk, he says. A question, since E-modulus is used in a conversion from measured strain into to bending moments, does the assumed value of elasticity modulus as opposed to actual one affects the identified influence line values?
I don't think I understood completely. Well, what was the relation between
since you're converting strains into the bending moment, which are forces, he's asking what is the influence essentially of elasticity models, the real one, as opposed to the one that is assumed as a theoretical. Is that a problem?
We always start from the theoretical modulus, although, well, sometimes we already know that it will be slightly higher. But with elastic modulus, especially when we calibrate the models, I think I said that it does not really mean that just the elastic modulus is 20% higher, because this can basically increase the modulus to unrealistic values. It just means that basically the stiffness of the elements that you are modeling is higher from different reasons. So one of them definitely is elastic modulus, but there are also others, from bending conditions, from temperature, anything that affects the stiffness in general. But it is most easily described by the elastic modulus. We discussed that also with Doron, who did the studies, and yeah, this is the most straightforward way of doing it, but we have to be aware of what is behind it.
Thank you for that. There is another question here coming up. Do you also have many challenges to install sensor and get data regarding your government? What are the procedures there? Is there any problem obtaining this data?
What was with relation to the government?
To the government, yes. Does government allows you to install sensor and to collect data?
I mean, we have, I haven't said that, but in Slovenia, we are performing bridge WIM measurements for 20 years, basically. And this means, because the bridge WIM is portable, it is done on more than 100 locations every year. So several systems are installed and deinstalled and moved to other locations. And this was agreed many years ago, and it's working quite fine. Of course, if you perform measurements on a specific bridge and you remove everything, you have to put it in the condition as you got it. So basically, those small holes that we bore into it have to be repaired. But this has not been a major issue until now. But in some countries, it is a bit more difficult. We are aware of that, yeah.
Okay. So the other question here is, what is the accuracy of axle load measurements? can we use it to find overweight vehicles? Is there a difference between rail and road vehicles? Two questions, actually.
Okay, we could have a full lecture on that. Accuracy, regardless of the Weigh-In-Motion system, depends on the installation. It's not about the sensor, it's about the Weigh-In-Motion system, which is sensor plus the structure. Structure can be pavement or the bridge. So it depends a lot. If you have a very smooth pavement, you can get very high accuracy of the results with both systems. If you have uneven pavement, if you have vehicles all over the place in the lanes, of course, the accuracy is far lower. Direct enforcement, which was the second part of the question, we don't do it yet, although CWIM, Bridge WIM is being certified according to OEML, which is the National Organization for Legal Metrology, which is the first step towards direct enforcement, but it is a very complex issue. I mean, it's being discussed for 10 years. There are some countries who are trying to use it with more or less success. My opinion is that it will still take some time, although some people do it. If you have ideal situation, ideal pavement, ideal bridge, some additional sensors that control temperature, that control location, then it probably can be done, but especially for bridge WIM, it hasn't been done yet.
The last bit of the question was the difference between rail and road.
The rail and road.
Yeah.
I mean, in theory and also in practice, rail bridge WIM is, I would say, better because, of course, you have the same truck, you have very smooth surface, while with the road bridge WIM, the trucks go left and right. The surface is not as smooth as railroad. So this alone basically makes a railway bridge WIM more accurate. Of course, you have different challenges because trains can be very, very long, which has different issues associated with it. But yeah, also railway bridgeway motion systems are expected to be more accurate because by nature they should be more accurate.
Thank you. There's one interesting question here as well. How do you convince bridge owners and managers to deploy a beam system?
That's a nasty one.
That's a nasty one, yes.
I mean, I can tell you the experience from Slovenia when it took probably, I don't know, probably 10 years to convince them that it is useful. I think finally they recognized, in particular after we saved them so much money, which this was also done in critical years after the economic crisis in the 2012, 2013, 14, when there was practically no money for maintenance. So they were quite happy with what they got. But then it primarily depends on people who are on the other side. So if they are open to this kind of new things, then it's pretty straightforward. While in some cases it's pretty hopeless. That's my experience at least. But if you are persistent, it may pay off in the end.
Let me allow myself a question, which may be also a nasty one, right? If you compare BWIM with a classical WIM cost-wise, right? Yeah. What would you say? You know, we have also WIM measurements that are in payment, as you probably know. There are different systems there, and they have BWIM. So, and the comparison on the price or price benefit or cost benefit ratio, what would you say?
I'm probably not the right person for it because I don't sell bridge-swim systems. So I don't know exactly what the situation is at the moment, but I would say, especially if you take, let's say, a longer period, so not just the installation, although even installation should be more cost efficient because first of all, you don't have to cut into the pavement, you don't have to close the traffic, you do everything from below. And in particular, later on, if you have to replace something, this is definitely cheaper than if you have to do all other things from stopping the traffic to grinding the pavement and so on. That's my opinion, but what is the actual situation at the moment? I must say that at least in the last 5 years, I'm not that much involved into that part of the bridge-swim scene.
But as you said before, there is a lot of potential onboard monitoring.
Yes, of course. Onboard monitoring is another topic which, I mean, in some countries, it's not that new. Australia has this access system in place for years, where the trucks which have the onboard monitoring active, they have incentives, so they can carry more load, but on very specific routes. It's coming. I mean, as I said, all the new trucks basically have it. I just discussed some days ago with some manufacturers. The point is that this is a feature that you have to buy. And of course, not everyone buys it because it's not needed at the moment.
Sure.
It
There is
can
one last.
be tempered, of course. So we say in the Weigh-In-Motion community that probably the best combination is the best way forward is combination of both, that they can check each other,
Calibrate
with cross calibrations, and then we will have really reliable information available.
There is one last question due to the time, and this is the question of multiple lanes and overtaking trucks, and are you able to accurately capture whether there is an overtaking of trucks on the bridge or not?
Well, it can definitely be taken into account. It is taken into account. It is calculated. There are procedures that, of course, there is a bigger error in this kind of measurements because, after all, you are calculating from the global response of all the bridges, of all the vehicles on the bridge. But we have quite efficient procedures that can deal with that. So basically, we say that the multiple presence on this kind of shorter bridges up to 30 meters, where you can have, let's say, one heavy truck in each lane, that is important. That is not a major issue. This can be dealt with without any problem.
With that, I would like to thank you for the excellent talk. I would also like to thank the audience for listening and staying with us for so long. I would also like to say that there is a recording on that, and you can also hear it on the YouTube anytime you want. You can also send the questions to either to Aleš himself or to the Eurostruck Secretariat. So please do so. And of course, finally, I would like to say that you are more than welcome to join Eurostruck if you want to do so. This is there is no cost to it, so just go ahead. And also, there is going to be a Eurostruck conference where we are probably going to welcome Aleš again, I hope at least. And this is going to be in September 2 to 5, 2025. And last but not least, our next live talk is going to be on November 19th, I'm sorry. So 19th of November. And we are going to host Maria Pinelli Moncelli as a speaker at that live talk. The moderation is going to be taken over by Elena Katzi. And with that, again, Aleš, thank you very much for excellent talk, and have a nice evening.
Thank you very much for listening.